Now I'm recording. So basically what we're going to do today is find the 6 trig functions and their ratios given a point on the unit circle anywhere. So what all this is saying is that let's say you traveled around the unit circle in clockwise rotations or counterclockwise rotations. But and no matter how far you traveled, positive or negative, wherever you stop on the unit circle, there is a unique point AB. And the distance traveled is going to be considered T units. So given the T units and the unique point AB, we can find the 6 trig ratios of that given point. So that's all these confusing paragraphs say. So basically, no matter how you travel around the unit circle, again, positive or negative units, this unique point AB, we can find the 6 trig ratios, and the sine of t, remember that sine is related to y, so this means sine of t would equal b of that coordinate point. Cosine of t would equal a of that coordinate point. And then the remaining trig ratios follow. Tangent of t would be b over a. Cosecant of t would be the reciprocal of sine, 1 over b. Secant of t would be the reciprocal of cosine, 1 over a. And cotangent would be the reciprocal of tangent, a over b. So again, keeping it simple, no matter if we travel positive units or negative units around the unit circle an infinite amount of times, no matter where we stop, there's a unique point AB that we can find the 6 trig ratios values of. All right, all good? Just a little definition for you. Okay. Which means let's go ahead and try that out on the next page. Given the point -1/2, comma, square root 3 over 2, given this point on the unit circle, find the 6 trig functions that correspond to t. So this means that if I start with, let me scroll down a bit. There we go. If I start with the sine of t, what numerical value would you give me?
Radical 3 over 2.
There you go. That's it. Because remember, sine relates to the y value. And then if I said, what is the cosine of t? What would you give me?
-1/2.
-1/2. And then if I said, what's the tangent of t? You would put
square root of 3.
Good. Is that what it reduces to?
Oh, maybe negative.
You'd put square root of 3 over 2 over -1/2, and then multiply by the reciprocal. And yes, you'd get negative square root of 3. Okay, which means if you have these 3 main trig functions, you can find the other ones. Jessica's already dead. Great. All right. So this means we'll go with the cosecant of t, which is the reciprocal of the sine function. So you're going to take the reciprocal of that coordinate. What are we going to get?
2 square root of 3 over 3.
There you go. 2 square root 3 over 3. And then if I said the secant of t, which is the reciprocal of cosine, what are we going to get?
-2.
-2. And then if I said, what is the cotangent of t, what are we going to have?
Negative square root of 3 over 3.
That's it. Negative square root of 3 over 3. And that's it. Nothing new, guys. So I guess the only thing new is we're finding the 6 trig functions values of a given point anywhere on the unit circle. But that's kind of what we've been doing already.
Just with the radians.
With well, with t units, right?
Well, but like previously.
Yeah, because we were doing it with angles, radians. Yeah.
Okay.
But like I said, nothing really has changed. We know how to find the 6 trig ratios. Okay.
So t is just like any random point. T or okay. So I was like what is like I was trying to
Exactly. Yeah.
Yeah.
So I mean, if I drew what we're looking at, right? Here's my lovely unit circle. All right. Well, first off, where would this point, what quadrant would this point be in?
5.
What?
2.
2? Did you say 5?
Yeah.
Okay, sure.
Come on, I try to make you laugh.
I was like, what? All right. So this point would be somewhere in quadrant 2 on the actual unit circle, right? So this would be the point, -1/2 square root of 3/2. And to get there, well, one, we could keep it simple. You start at the right side of the unit circle, and you would travel t units to get there. So you're basically traveling around the unit circle. So this would be t units. But my units could go any way they wanted. I didn't have to just travel from this point to that point. I could actually traveled around the circle an infinite amount of times and still landed at that same point in the second quadrant. So basically what that first page is saying is that no matter how many t units you go counterclockwise or clockwise, positive or negative, no matter where you land, there is a unique point that belongs to the distance you traveled at. That's it.
So is t just like equivalent to like any like random angle that you're given?
Not yet. So t is just distance. So t is just right now, t is distance around the unit circle, positive or
Distance
negative.
on the unit circle, like on the line of the unit circle.
Exactly.
Okay.
That's
got
it. Yeah.
So it's kind of like an arc length.
Yeah, you can consider it an arc length.
Bro.
Okay. All right, which means next example, do the same exact thing. So given p is square root of 5/3, comma 2/3, find the 6 trig functions. So say sine of t, what do you give me?
2/3.
2/3. Cosine of t, what do you give me?
Radical 5/3.
Radical 5/3. And then not cotangent. Yeah. Tangent of t.
Square root of 5/2.
Square root of 5/2. All right. Can anybody verify that?
It's for show. I got you.
Mm-hmm. All right. What else? Cosecant of t gives me what?
3/2.
3/2. And then secant of t gives me
3 square root of 5/5.
3 square root of 5/5. And last, cotangent of t gives me
2 square root of 5/5.
that's it. All right. And there you go. So we are able to find the 6 trig values of a given point on the unit circle that corresponds to some distance t, some unit of t. All right. Any questions on that page?
Wouldn't the tangent be 2 radical 5/5, or did I mixed up in my head?
Ooh, I told somebody to fact check it. So
No disrespect to
tangent,
Lewis, I might be mixing up my head.
so
Wait,
tangent would
no,
put
he's
the
right,
2/3
sinus y, not x.
over. So tangent would put 2/3 over square root of 5/3, right? And then you'd multiply by the reciprocal. Oh, somebody's in trouble.
Hey, y'all should have listened to him.
And you get 2 over square root of 5. That just lets me know who's paying attention.
I threw y'all a curveball.
Over 5. Oh my goodness. We were lied to. Blame this one on Jessica. All right.
And Jessica, what the heck?
Which means what is cotangent then?
So that's going to be your radical 5/2 then?
There you go. Cheat codes, right? Step back one and flip it. All right, there we go. Now it's fixed. Oh boy. All right, good catch, Ethan. Okay. All right, so next is the trig functions of any angle. Since the values of the trig functions of an angle theta are determined by the coordinates of the point AB on the unit circle corresponding to theta, the units used to measure the angle are irrelevant. So to find the exact value of a trig function of an angle requires that we locate the corresponding point AB on a given circle whose center is at the origin, x squared plus y squared equals r squared. So for an angle in standard position, we let AB be any point on the terminal side of theta that is also on the circle x squared plus y squared equals r squared. So what all of this is saying is that no matter the radius of the unit circle, let's say the unit circle, we were given a unit circle with a radius other than 1. No matter what, we could still find the 6 trig ratios based on that point and based on that radius. So that's all this is saying here. And our ratios remain the same. So if I were to draw this out, here's our coordinate plane. And then let's say that here's my unit circle of any radius r, and we were given a point AB. So I'll put it here. I'll just put it in the first quadrant. Here we're given a point AB. Well, given this point, we can find the 6 trig ratios if we make our angle in standard position, meaning centers at the origin, initial sides on the x-axis, and terminal side is anywhere inside the unit circle. So here, terminal side is just going to be in the first quadrant. So what we can do with that is, of course, make our right triangle, where here our base is, what do I have? A, B, yes. So my base is A, my height is B, and my unit circle of any radius is given by R. And if we have the right triangle filled out and we know the radius, this means we can find all of the values of the 6 trig functions. That's it.
So it's just a different way of like writing it, kind of
Exactly.
like in the last class, like with the x, y, r, and then just.
Exactly. So just another way of writing it. Like I said, we're not really learning anything new. We're just adding on to what we know already.
Okay.
Yeah. And because I guess what we've been really finding is ratios within the unit circle. Now, what this definition allows us to do is find ratios given any unit circle with any radius. Hence the x squared plus y squared equals r squared, because r can be any radius it wants now,
And
other
when
than
you say
1.
any unit circle, you mean like any point on the unit circle?
Both. Because remember, the unit circle we work with, the radius is only 1. But with this definition, it says, hey, what if we are given a unit circle where the radius is 5? And no matter the radius, you can still find the 6 trig ratios.
Or would that still make it the unit circle?
It'd be a form of it.
Okay.
Yeah.
I got. I mean, I got you.
It would just be a form of it. Yeah. All right. Uh-oh. Restart request retire. I didn't request a restart. Oh well. Okay. So with that being said, find the exact values of an angle if the point negative 1 is a point on its terminal side. Okay. So we definitely want to draw this out because we want to know what quadrant we lie in. So here, draw my little coordinate plane. And where would negative 1 be? Which quadrant?
3.
Quadrant 3. So here, oh, come on. Here, I'm going to draw my initial side. There's my initial side. And then down here, we know we're in quadrant 3. And this point will be my negative 1, which means we can form our right triangle. Here would be my angle of theta, and the height is negative 1. The base is negative 1, which means if you have the height, if you have the base, this is a right triangle. We use the Pythagorean theorem to find the hypotenuse. So what would my hypotenuse be?
Radical 2.
That's it.
Yeah, square root of 2.
Square root of 2. And now we have all 3 sides of this triangle filled out. And hey, this is saying that the radius is the square root of 2. So now again, you're messing with a different type of unit circle. But that's just to show you how the definition works. For now, we fill out the triangle. You can find the 6 trig ratios. So with that being said, what would the sine of theta be?
Negative square root of 2 over 2.
Good. Negative square root of 2 over 2, right? You get negative 1 over square root of 2, which would be negative square root of 2 over 2. All right. What would the cosine of theta be?
Negative square root of 2 over 2.
Same exact thing. And then what would the tangent of theta be?
1.
1. Good. Tangent of theta would be 1, which means let's get into the reciprocal functions. What would cosecant of theta be?
Negative radical 2.
That's it. What would the secant of theta be?
Same thing.
Same exact thing. And what would the cotangent be?
1.
1. And that's it, guys. I guess something cool you can pull from all of this is that no matter the radius of the unit circle, so here for this problem, the radius is the square root of 2. But no matter the radius, you still come out with trigonometric values that match the ones of your original unit circle. So, oh, that should be negative. There you go. Because if you look at your unit circle, look at, what is it? 5 pi over 4. That should be in quadrant 3, right? Look at 5 pi over 4 right there. And what would the cosine and sine be of 5 pi over 4?
Negative square root of 2 over 2.
Negative square root of 2 over 2. Is that what we just found?
Yes, sir.
And this unit circle happens to be with the radius of 1. But you see the comparisons.
Well, wasn't the other one technically also with the radius of 1?
Which one?
Oh, no, never mind.
Yeah. So you're gonna get similar values with your trig functions, no matter what the radius is. So this is why we can find the six trig functions of any angle. Yeah, cool stuff, right? Okay. Any questions on that before moving on? All right. Okay. Now we come across the periodic properties of trig functions, which is really important. So the periodic properties mean, what is it? How many times, or what is the repeat cycle? There you go. I'm trying to keep it simple. What is the repeat cycle for each trig function? So how many revolutions does it take for a trig function to repeat the same numerical values? And for the four trig functions, sine, cosine, cosecant, and secant, these all have a period or a cycle of 2 pi, meaning that no matter how many revolutions you do, you will always end up at the same value. And it's only for sine, cosine, secant, and cosecant, as you see from the picture above. So these functions repeat themselves every 2 pi. So if we were to start at AB here and did a whole revolution of 2 pi, we would still arrive at that same point, AB, no matter what, for those four functions. Okay. The only two functions that are different are tangent and cotangent. These functions have a period or a cycle of pi. So these functions repeat themselves every pi. So here, if you have a point AB and do a cycle or a period of pi, you'd arrive at the point negative A, negative B. Well, remember, tangent puts opposite over adjacent. So tangent is positive in the first quadrant, which means if you do a cycle of pi, tangent's also going to be positive in the third quadrant. So tangent and cotangent repeat themselves every pi. The other four functions, sine, cosine, secant, cosecant, repeat themselves every 2 pi. These are their cycles, these are their periods. And it's going to come in handy when we actually start graphing these functions. Not yet, though. Okay. So for your periodic properties, this is kind of like coterminal angles. If you notice that your function is over a revolution or under a revolution, you're going to add 2 pi or you're going to subtract 2 pi if it's in radians. If it's in degrees, then you're going to add or subtract 360 degrees. And this will be the same for these four functions, because all of these functions have a period of 2 pi. The only ones that are different is, again, tangent. If you notice that tangent is over a revolution or under a revolution, you're just going to add pi or subtract a pi if it's in radians. If it's in degrees, then you're going to add or subtract 180. Okay. So these are the periodic properties for the 6 trig functions. So sine, cosine, secant, cosecant repeat themselves every 2 pi. Tangent, cotangent repeat themselves every pi. Any questions on that? Okay. So let's go ahead and try out these periodic properties. So we want to find the exact value of the sine of 420 degrees. Is that over a revolution?
Yep.
Yep. So we would subtract 360 because we're in degrees. And the sine of 420 degrees would be equivalent to the sine of what?
60.
60. And looking at your unit circle, what is the sine of 60 degrees?
Square root of 3 over 2.
Square root of 3 over 2. There you go. Okay. All right. Next is the tangent of 5 pi over 4. Okay. Well, 5 pi over 4 is within a revolution of 2 pi. You can see it on your unit circle here. But we want to practice periodic properties. So if I have the tangent of 5 pi over 4, this means I went over a cycle of tangent, which means that instead of subtracting 2 pi, I'm going to subtract what?
Pi.
Pi. So this would become the tangent of 5 pi over 4 minus pi. You'd put pi over 1 and get a common denominator of what?
4.
4. So this would be tangent of 5 pi over 4 minus 4 pi over 4, which would give us an equivalent statement of the tangent of what?
Pi.
Pi over
4.
4, which is over here. Which means that what is the value of tangent at pi over 4?
1.
1. That's it. Which would be the same value as the tangent of 5 pi over 4. Because if you look at 5 pi over 4, if you put those coordinates over each other, you're still going to get what answer?
1.
1.
1. But again, we wanted to practice periodic properties. So we wanted to show that tangent does repeat itself every pi, and we have just proven that it does so. So from pi over 4 to 5 pi over 4 would be a period for tangent, a period of pi for tangent. But no matter what, you still get the same numerical value. Okay. Cool. All right. Cosine of 11 pi over 4. Is that over a revolution? Well, if you look at your unit circle, what's the last pi over 4 that you see?
7 pi over 4.
Oh, it is, yeah.
7 pi over 4. So would 11 pi over 4 be over a revolution?
It would.
Yeah, and it's past 8.
It's definitely past 8, right? So we could do our trick. Remember, we've learned all this pre-cal up to now, so we can do our radian trick as well, where you can find the coterminal angle of 11 pi over 4, which means you can do 4 into 11 pi. And how many times does 4 go into 11?
2.
2. So it'd be 2 pi times. You'd have 8 pi with the remainder of 3 pi. So this means that we have 2 pi plus 3 pi over 4, which means that the cosine of 11 pi over 4 is the same as the cosine of what?
3 pi over 4.
3 pi over 4. Now look at your unit circle, and what is the value of cosine at 3 pi over 4?
2 square over 2.
Good. Negative though, right?
Hmm.
There we go. Okay, cool. Also, you can count radians, right? This would be 7 pi over 4. This would be 8 pi over 4. This would be 9 pi over 4, then 10 pi over 4, and then 11 pi over 4. Fun stuff. Okay. Secant of 540 degrees. Is that over a revolution?
Yep.
Oh, yeah. Good. So you'd subtract 360. And you'd get the secant of what? What is that?
180.
Is that 180? All right. So 540 degrees is the same as 180 degrees. And what is the secant at 180 degrees?
-1.
-1. Good. Done. Okay. And those are your periodic properties. So again, remember, your takeaway is that sine, cosine, cosecant, and secant, they repeat themselves every 2 pi. Tangent and cotangent only repeat themselves every pi. Everybody good with that page?
Yep.
Hey, we lost a lot of people. Where are they going? St. Patrick's Day is not till tomorrow.
They blew this popsicle stand.
Okay. Well, next is the even and odd properties of your trig functions, which is also important. So remember what it means to be even and odd? This is an algebra review, right? So to be an even function, algebraically, this means if you plug in -x for every x, you'll get the original function back. That's algebraically. Graphically, to be even, you are symmetric about the y-axis. You guys remember that?
Nope.
All right, perfect. To be odd, algebraically, means you plug in -x for every x, and you get the original function back, but everything is negative. Or not everything is negative, but all your signs have changed. And that's algebraically. Graphically, if you're odd, you are symmetric about the origin. Okay, well, we can apply these algebraic properties to trig functions, of course. Now, if you look at this chart on the left, the only even functions are going to be cosine and secant. Because when I say the cosine of -θ, I get the cosine of theta back, which means I get the original function back. The secant of -θ becomes the secant of theta. So
Can
the
you show
only,
us, like, why that works?
oh yeah, I'll show you in a second why that works. So the only even ones are cosine and secant. So what would be good with that? If you're symmetric about the y-axis, let's see, especially with cosine. Okay, let's use this unit circle to show why. All right. Let's say I wanted the cosine of pi over 6. What numerical value would you give me?
Square root of 3/2.
Square root of 3/2. Okay. And then let's say I wanted the cosine of -pi over 6. What quadrant would that put you in?
Two.
-pi over 6. So remember, if it's a negative angle, you go
So 4.
clockwise. So cosine, well, -pi over 6 would put me in quadrant 4.
So that'd be 11 pi over 6.
It would technically be 11 pi over 6.
Technically.
technically, which means what is the x value at cosine of negative pi over 6?
Square root of 3/2.
Square root of 3/2. Hence why we say cosine and secant are the only even functions, because no matter if you plug in a negative angle, you're going to get the same output. That's why we can say by the even and odd properties above, the cosine of negative pi over 6 is the same as the cosine of pi over 6 by even properties. Because do we get the same numerical value?
Yes, sir.
Does that make sense? All right. So that's why cosine and secant are the only even ones. And secant's even because secant is the reciprocal of cosine. Okay. And guess what? The remaining 4 trig functions are all odd. Sine of negative theta is negative sine theta. Cosecant of negative theta is negative cosecant theta. Tangent of negative theta, negative tangent, and cotangent negative theta, negative cotangent. So I guess if you want to remember who's even and odd, just remember that cosine and secant are even and the rest are odd. That's probably the best way to remember it. Okay. Any questions on that? And also to prove it would be when we graph it next class. You'll see that cosine is symmetric about the y-axis, and you'll see the other 4 functions are symmetric about the origin. All right. Okay. So using our even and odd properties above, let's go ahead and find the exact values of these trig expressions. So the sine of negative 45 degrees. By the above, how could I rewrite this trig expression?
So regular 45 degrees, it would be the square root of 2/2. So just negative square root of 2/2.
Well, when we get there, I'm asking you to take this and rewrite it as that using the chart.
Negative sine of negative 45.
Well, remember, the negative comes out because it's odd.
Negative sine.
There's sine of 45.
So negative sine of 45. And now you find the sine at 45 degrees and apply the negative to it. So what was that numerical value?
Negative square root of 2/2.
There you go. That's it.
Honestly, it kind of feels like extra work to me.
I mean, I guess I would agree, because some of these properties are like, hey, why not just find out where the sine of negative 45 is and give me that answer? But we are showing other techniques on how to find those values in case you come across something a little more difficult.
Gotcha. Just go over everything then.
Exactly. Like we're covering all our bases.
Is there?
Because where would the sine of negative 45 degrees be?
Fourth quadrant.
Fourth quadrant. You'd be right here at technically 7 pi over 4. And what is the y value at 7 pi over 4?
Negative square root of 2/2.
There it is. So we could keep doing that, but that means trig would be too easy, right? Maybe because it is. All right. The cosine of negative pi by the even and odd properties above. What is another way to rewrite the cosine of negative pi?
See, I was thinking 1, but it makes like no sense to me because, if I go across and then, I reach pi, negative pi, it's negative 1. Oh, but then if I were to do the cosine of pi, it's negative 1 as well. Oh.
You're going too deep. I just want you to rewrite it using the properties above.
I'm sorry.
So cosine of negative pi can be rewritten as what?
Cosine of pi.
That's it. And what's the cosine at pi?
1.
-1.
-1. And you could even prove that with the even and odd properties. Because if you go negative pi, that means you do a negative rotation, right? So you do negative, and you'd end up here at negative pi. But it just so happens that even if you had the cosine of negative pi or the cosine of pi, the numerical answer is always going to be what?
-1.
-1. There you go. See, these properties are there to make you think. All right, cotangent of -3 pi over 2. Is cotangent even or odd?
Odd.
Odd. So I can rewrite this as the negative cotangent of 3 pi over 2, which means look for 3 pi over 2 on your unit circle and give me the cotangent of these coordinates. What does cotangent do? Does it put x over y or y over x?
X over y.
X over y. So it puts 0 over -1, which is
0.
0. -0.
-0.
That's not a thing.
It's just 0. Hey, quadrant 5 was a thing earlier.
I regret everything.
It is a thing, all right.
Quadrant 5. Sure. Okay. Last one. Tangent of -37 pi over 4. Is tangent even or odd?
Odd.
Odd. So we can rewrite it as negative tangent of 37 pi over 4. Oh my goodness. Is that over a revolution?
Oh, yeah.
Yeah.
So we could do our little trick here. 4 into 37 pi goes how many times?
9. And you're going to have a pi over 4 left over.
And so that puts you in quadrant 2.
So 9 pi plus pi over 4. So this means that this becomes the negative tangent of pi over 4. So what are we going to have?
Square root of 2 over 2.
One.
Tangent at pi over 4 is, why don't
Sorry,
you
I'm
just,
so sorry, sir. Okay.
Would it be -1?
it'd be -1. Good. Well, tangent at pi over 4 is 1, but what's waiting on the outside?
Well, wouldn't it be -1? And then it would change to 1.
No, it's going to be -1.
No.
There you go.
Because, wait, okay, no. Oh, no, because tangent -30. Oh, wait. Okay, I'm sorry. I don't know. I'll do it. I'll do it.
Look at that brain going a million miles.
Lewis, I want those 30 seconds of my life back.
Sorry. It's that big burger I ate earlier, man.
There you go. -1. Okay. Cool. So that's it, y'all. That's 7.5. Nothing crazy, I told you. Some things new, other things just we know, just threw a little more on top. So other than that, we are done. So if you got questions, stick around. If not, I'll see you on Thursday.